Okay, we're going to look at remotely connecting to an acoustic interferometer at Arizona State University so that we can remotely collect data. And this is associated with a physical chemistry online lab. Information about this can be found publicly at biopchem.education. So the first thing we're going to need to do is remotely connect to the system, and in this case, the computer that's running it at Arizona State University. There are two ways to do this. One is with no machine, and the other is with AnyDesk, and we'll look at AnyDesk being the easier to set up and more commonly used one. So this is the AnyDesk window. You can connect to a remote system. The ID, the AnyDesk ID, is given at biopchem.education. The password for students in ASU Online Chem 343 is provided on the official Canvas website, and for anyone publicly, they can email and receive the current password to be able to access the system. So I have it bookmarked here, and I have it where it automatically logs the password because I've already logged into it once before. So now I'm in AnyDesk, and I am on the system here. Here I am from my MacBook computer, logged in, and I'm looking at the desktop as though I was sitting in front of the computer at Arizona State University. So the other way to access it is with no machine. It's a little more advanced. You need to be on the ASU VPN to be able to do this, and it can take some additional sound manipulation because by default, no machine tries to route the sound through the remote VNC. The other ones we have here is we have a web browser, and in this web browser we've bookmarked them here. They're already open. We have a live view of the acoustic interferometer. So this is showing both the acoustic on the home view. It's showing both the differential scanning calorimeter and the remote acoustic interferometer, both which you can remote into and run remotely as though you were in front of the instruments directly. If we use call 1, it zooms in on, oh, that's the wrong one. Call 1. Yeah, it zooms in kind of on the entirety of the acoustic interferometer. Call 2 zooms in on the flow of the gas, and we have several other calls that zoom in on different parts of this so that you can see very explicitly what's going on. And we can see that we're controlling the computer as though we were sitting at this in this lab directly, and there's a little bit of a lag, but if we move this, you'll see on the screen in that computer, it's moving as well. So we're controlling the computer as though we're sitting there. One thing to also notice is that multiple people can log in, and then you're almost fighting for control. So we try to set up where we have a schedule so that people can schedule time where they won't be interrupted, and they can use this exclusively or log in as teams, but know through Zoom or something that who's controlling it so that somebody isn't getting in and trying to fight for control and multiple people are trying to do measurements at the same time. Okay, and that's that one. The second tab over here is the web thing to be able to control the gases, so you can choose which of the gases there are and then for how long it goes, and you can purge it. You can go back here and we'll zoom in to call 2, zooms into this flow meter, which is flowing into the system. Right now it's not flowing. And if we go to air, which I recommend for all just kind of tests, and hit purge for 20 seconds, go back to the live view, we'll see now it's purging, and we can read this is in liters per minute. So it's somewhere a little around 2 liters per minute is what it's flowing. It'll flow for 20 seconds and you'll see this go off. We can further, if we look at some of the further calls on this to get a sense for what's going on. Like we have one where we can see one of the gases and then what the temperature and humidity is in the room. We can zoom in on one side of it, which is where there's a hole here, and then this is where the microphone is. Call 7 should be the other side. Yeah, so this is just an earbud that has a little Teflon tape in it to hold it, and a little needle here where the gas is flowing in, flowing out the other side. And again, if you go back to home, it'll kind of show you an overview of everything on that lab bench, and call 1 is an overview of just the acoustic interferometer. So we have a computer here that we're logged into running. Above that is the gas control. It has several valves that flows into here. We can generate sound through this earbud speaker here. We can collect the sound on this microphone on the other side. For context, this tube length is about 2 feet or 24 inches. We can measure it very accurately by using a known gas like this argon tank, flowing it in here where it has a very well-known speed of sound, and therefore calculate very accurately what the length is, and then use that length, which doesn't change as you flow different gases. For example, an unknown gas where you would want to determine what the speed of sound is. We have it hooked up to several house gases, air and nitrogen, as well as this argon tank, and then we substitute out different unknown refrigerant gases that students determine what the composition of that gas is through determining its speed of sound and its associated thermodynamic properties, and what is consistent with that, those properties. They can identify what the different unknown gases that we hook up to the system are. Okay. So the next thing now we need to be able to do is generate sound, and we'll use the same system to generate the sound. You can, in this case, white noise, for example, and be able to record what comes as it resonates through this cavity with different gases in it. So for that, right now, we're using Audacity. Which is a freeware program. I recommend that all students have this on their own computer as well. The only thing we're going to use it for here is just to collect the data. Then you can download this data and do all of the rest of the data processing and stuff on your own desktop Audacity. So right now we're just going to use it to record stuff. It defaults to a sound rate of 48 kilohertz. This is usually the biggest issue, is there's often several sound devices, and you have to make sure that it's selected for what is the earbud speaker here and the lav mic here, which are these USB plugged in audio devices. This can sometimes get messed up when you go in through no machine or even AnyDesk or anything. You can often try to reroute the sound through the VNC. So this is one area where people can try to change this, but this is set to what should be the correct audio at the moment. What is the proper rate to use? Well, we can look at it and determine. So we've already flown some air through the system. So let's generate. We'll start. You can do this either generating chirp noise, or what I'll show you this time is white noise. So we'll generate some white noise at half amplitude or 50% amplitude for 30 seconds is reasonable. So that generates some white noise here. How do we know it's white noise? Well, we could analyze it and look at its spectrum, and sure enough, it's half of the project rate, and it's pretty evenly distributed across the entire range. So what we would define as white noise. And now what we want to do is play that noise while we record on a new track. And we can do this mono. We just need one channel for it. We don't need to do it in stereo. And so the easiest way to do that is to go to Transport, Record, Record New Track. And then it will record off this while it's playing off here. So it'll play whatever you've generated on this first track through this speaker, and it'll record here. And so it's generating white noise, and it's recording something that, you know, you really can't tell till you analyze, but looks fairly white noise-like. So we'll let it record. We're not flowing any gases at the moment. It's just the gas that was left over from when we did. And now it's no longer generating noise, and so you can see this is in a sense the background of the mic when there's no noise being played through the speaker. And so we'll record a little bit of that. So now if we analyze this, we'll see we're analyzing it. It's a linear rectangular filter, 32,000 points filled out. That's more than we need, but you'll see why we don't need such a high project rate. Like this thing dies off before half of the project rate, and you can tell we could end after about 5 kilohertz or so. We have data all the way out to about 15, but usually you don't need more than about 10 to 20 resonant modes. And so on top of that overall white noise are these resonant modes that have to do with the speed of sound, or the gas that's in it and its speed of sound, and the length of the tube. So this gives us the indication that we could change our project rate and collect white noise at a lower rate. So what I'm going to do is save this, just so anyone who wanted to look at this. Today is the 21st. It's the remote acoustic interferometer, white noise. We're not doing chirp, and we're not doing multiple gases here, so we can, and at 48 kilohertz. And just for completeness, we'll say it's air. Okay, so we can save that. It's saving in this acoustic interferometer data set on this computer. We can talk about how to get it off later, so we'll just save that. Now we have that saved. We could come in and name these tracks, etc., but we have that data saved. So now, actually, I'll just close everything. We'll start fresh again. Open full screen. It kept, this time when it opened, it kept the right audio. That's good. We're going to lower the rate to 11 kilohertz. We're going to generate white noise, and just for, we saw we easily had good enough data, so I'm going to do this for 11.025 seconds, which isn't critical for the white noise, but it's sometimes nice to have things about the same number of seconds as the project rate when you're doing chirp noise, which we can discuss later. So now we have that. You can click up here. It's sometimes hard to do this remotely, but you can change the name of it here. White noise. Oh, 2E's. Let's just leave that. We can change that later. We get this sense. So, and then while we're flowing a gas, so again, we'll just flow air, and we'll do it for 30 seconds just to give ourselves time. So we'll flow air for 30 seconds. We'll make sure it's actually flowing. Doesn't look like it is. So this is a good time to see what we can do to diagnose this. So one of the things I often do is to reload the host here. We'll click, say 20 seconds, hit purge again. Yeah, there it is now. So it gives you a sense that it gives you a live view so you know you actually are flowing gas. So while it's flowing gas, we can record on a new track. We could have adjusted the volumes if it wasn't on scale here. That's sometimes something you need to do. You can see it stopped flowing while we're still collecting, so we probably, for consistency reasons, we can stop this, get rid of that track, go back to the beginning, and flow again. So purge and see if we can get this started so that we're recording data the entire time gas is flowing for consistency. So it's flowing gas at 2 liters per minute, and we're collecting on the microphone while white noise is going through it. And we can even see here, like, where it stops. Now we're just collecting background where there's no flow or no noise being generated. So, and we've done it at a lower rate. We've done it while flowing gas. So we can just briefly look at this. Again, all of this, plotting the spectra, analyzing it, can be done after the fact. You just need to get on the remote system, but just to make sure the data we're collecting looks reasonable, it does. We see the nodes, enough to easily analyze this gas, for this first gas. So we can now mute this because we don't want to play it. We just want to play white noise, and we could flow a different gas through it and collect data. So we'll do one more just to show, and students can of course do all the different gases connected. So we did air. Let's also do argon, for example. So we can flow argon for 20 seconds. Let's make sure it's actually flowing. It is about the same, 2 liters per minute. So I'm going to let it flow for 20 seconds and get this one ready to collect for the next time. So if I can get this clicked, which remotely it's sometimes really hard to do. Yep, I'm not having good luck. I'll have to do that as I download it. So it ended. I'm going to do it again. Make sure it's flowing. And then here, I'm going to record to a new track. I'm playing the white noise. I'm recording on this track. This one's muted, so it's just doing the same above, and it's still flowing the entire time. You can even see here it was still flowing. There's a little noise from the flow, and then this is just background noise. So I'll collect a little background just so I have a consistent set of data. And now I've collected 2 of the gases. Okay, let's show one other technique for completeness. So we've just flown argon through it. I could mute this. I can generate chirp, and I'm going to generate it with a higher amplitude in the beginning because it'll be lower amplitude of the recorded sound at low frequency, and then it's linearly going to go to less of an amplitude. It's going to start at 1 hertz. It's going to go to 5,512.5 hertz, right? So half of the project frequency, so that I would, in a sense, get the same number of nodes that I would from the white noise. I'm going to do it for exactly 11.025 seconds so that it's easy to map frequency, time into frequency. So I can generate that on a new track if I want. So what I'll do is go to the beginning. I will go to add a new track, a mono. Oop, did not mean to do that. Track, add new, mono track. So now I have a new track here. I'm going to generate on that track the chirp that we just saw. So this, that looks right. It starts at high amplitude, goes to low. We could zoom in and see the frequency here. Everything else is muted. So this is the only one playing. I can go to the beginning of that. I can flow argon for 20 seconds again. Make sure it's flowing. Go to the beginning of this track and tell it I want to record a new one. And here we see it more directly because we're chirping linearly through this frequency range. So we're seeing the resonances more directly. Here you have to Fourier transform or get the spectrum to see it. So this is an alternative method to get the same type of acoustic interferometry data. And I would argue more direct and a little more elegant a method. Okay, I think that shows some of the basics of this. With this, let's always, save your project. So we saved just the air one at 48 kilohertz. This is now at 11 kilohertz. And we did white noise and chirp. And we did air and argon. And I know it's creating this. This is one of the annoying things about AnyDesk. Sometimes it does kind of multiple characters. I'll correct this when I download it, just like I'll add the labels to these various ones once I download it on my own computer. So I'm saving that again. So now I have this data saved. Just to make sure no one writes over it or anything, I'll just go ahead and close it. So when you open up Audacity again, it'll open up a new window so that a new person can start fresh and not save over your data or anything. We're leaving it, I like to leave the acoustic interferometer on air because we don't want to waste argon or other gases. So I usually make sure it's still flowing well. I'm within my allotted time here, and I'm scheduled for our office hour as well, so students can sign up here. It also has an information page on this Google. And then lastly, we could go to the ASU Chem 343, which all students have access to, and we could go to the drive and we could take that data and put it under the drive so that we have it shared with all our other students and we have access to it remotely. Another way to do this is in AnyDesk. It has a file manager in it. So I can go, it shows me the remote computer and we can see the data we collected right here and right here, and we can download that data to our local computer. It's downloading it to my downloads directory. And then I can open it in Audacity on my own computer and do all the analysis, etc., which I'll follow up with in another video. So hopefully that gives you a quick overview of our latest development version of the remote acoustic interferometer and how to get onto it and be able to collect data remotely. Thanks.